Okay, so this is the more difficult portion of Chapter 7, and probably the most difficult portion of the CS141, 241 sequence. And we're going to do a little bit more looking at linear recurrence relations and, in particular, how to solve. And I had the occasion to visit Taiwan quite some time ago. You can see I look a little bit different, a little younger. And the airport in Taiwan has a whole bunch of Hello Kitty theme, and there's all kinds of different activities. This is obviously the last 5 minutes of shopping before you get on your plane. Um, but they also have how to draw Hello Kitty. And how to draw Hello Kitty basically takes 6 steps. And I figure, well, if you can draw Hello Kitty in 6 steps, then, you can put together the steps to solve a linear homogeneous recurrence relation because that also takes 6 steps. They're different, but it's important to be able to draw Hello Kitty and to be able to solve these. Um, and, of course, 7-Eleven Malaysia also has different things that you can solve with Hello Kitty as well. So, a linear homogeneous recurrence relation of degree k with constant coefficients is a recurrence relation of this particular form. And here the c's are constants, the a's are the terms of the linear homogeneous recurrence relation. And linear basically means that it's the sum of previous terms multiplied by a function of n. And homogeneous means no terms occur that aren't multiples of the previous terms, and the coefficients are all constant. So that makes our job a little bit easier. I sure wouldn't want to find a solution to this off the top of my head, but we'll see a clear pattern in how we actually solve these based on the number of previous terms. So some of the terms are the degree. So for example, P sub n is equal to 1.11 times P to the Pn minus 1. That's a linear homogeneous recurrence relation of degree 1. You might use that for something like calculating interest. F of n is equal to f of n minus 1 plus f of n minus 2. That one you may recognize as the Fibonacci sequence, and that's a linear homogeneous recurrence relation of degree 2. A sub n is equal to the fifth previous term. That's a linear homogeneous recurrence relation of degree 5. So the next one is not linear because we have a squared term. The next one is not homogeneous because there's different terms that are constants in terms of the addition. And there are also ones that don't have constant coefficients, like b sub n is equal to n times b sub n minus 1. And, the ones up in the degree bullet point you'll probably recognize. So basic approaches to solving these, look for solutions of the form a sub n is equal to r to the n, where r is a constant. So a sub n is equal to r to the n is a solution of the recurrence relation a sub n is equal to c1 a n minus 1 plus c2 a n minus 2 all the way out to c sub k r n minus k. If and only if r sub n is equal to c1 times r to the n minus 1 plus c2 r to the n minus 2 plus c sub k r to the n minus k. When we divide both sides by r to the n minus k and subtract the right-hand side, we get what's known as the characteristic equation. The characteristic equation is going to be the key to solving these. So let C1 and C2 be real numbers. Suppose that r squared minus C1r minus C2 is equal to 0, and it has two distinct roots, r1 and r2. And you probably recognize that form of equation from the quadratic equation. Then the sequence a sub n is a solution of the recurrence relation a sub n is equal to C1 a n minus 1 plus C2 a to the n minus 2, if and only if a sub n is equal to alpha 1 r1 raised to the n plus alpha 2 r2 to the n for n is equal to 0, 1, 2, where alpha 1 and alpha 2 are some kinds of constants. And the proof is actually quite a mouthful, and it doesn't work the same way when r1 is equal to r2. notice that this one is an if and only if, so that means that it's biconditional. So we have to show both ways. So what is the general outline for solving these? The proof is in the textbook if you want to look at that. But the general outline is probably the most important thing. Basically, the first thing we want to do is determine the characteristic equation. Then we want to find the roots of the characteristic equation. Use the appropriate theorem to write the form of A sub m with the alphas. Use the initial conditions to get the equations for the alphas. And then solve the equations from step 4. And then we use the appropriate theorem again. So let's take a look at an example. This is Charmy Kitty. It's not Hello Kitty. But the example itself is actually written. So we want to solve A sub n is equal to A sub n minus 1 plus 2 times A sub n minus 2. And we have some initial conditions. A sub 0 is equal to 2 and A1 is equal to 7. So what we do is we get the characteristic equation. And you'll notice there's a constant 1 in front of that A n minus 1. So we get r squared minus r minus 2. Now that's a quadratic equation, and we can actually solve that and find the two roots. The roots end up being 2 and minus 1. Now we use theorem 1 to write A sub n is equal to alpha 1 times 2 raised to the n plus alpha 2 times minus 1 raised to the n. Step 4. Use the initial conditions to get equations with alpha 1 and alpha 2 isolated. So here we know that 2 is the 0 term and 7 is the 1 term. So alpha 1 times 2 raised to the 0 plus alpha 2 times minus 1 raised to the 0 is equal to 2. So that tells us alpha 1 plus alpha 2 is equal to 2. Then we do it with the ones. Alpha 1 times 2 raised to the 1 plus alpha 2 times minus 1 raised to the 1. And we get 2 minus 1, 2 alpha 1 minus alpha 2 is equal to 7. Now, that's a set of simultaneous linear equations, and we can use that work that we did in section 3.8 on solving matrices to solve that, or we can solve it as two equations and two unknowns. And basically we solve those and we get alpha 1 is equal to 3, alpha 2 is equal to minus 1. And then we use theorem 1 again with the actual alphas that we computed, and we get 3 times 2 to the n plus minus 1 times minus 1 raised to the n, and we can further simplify that last term. This gets it in the format that we want, and then we can actually directly compute any A sub n. Okay, how about for the Fibonacci numbers? Here we have f of n is equal to f of n minus 1 plus f of n minus 2 with f of 0 is equal to 0 and f of 1 is equal to 1. That's the classic Fibonacci sequence. We use the same general outline, those same 6 steps. So what is the characteristic equation here? Well, it's r squared minus r minus 1. Now we can find the roots again using the quadratic equation, because that one doesn't solve itself simply algebraically. So I just use the quadratic equation, and we get 1 plus the square root of 5 divided by 2 and 1 minus the square root of 5 divided by 2. And those actually turn out to be phi and phi complement. Use theorem 1 to write f of n is equal to alpha 1 times 1 plus the square root of 5 divided by 2 raised to the n plus alpha 2 times 1 minus 5 1 minus the square root of 5 divided by 2 raised to the n. Use the initial conditions to get the equations with alpha 1 and alpha 2. So we know f0 is equal to alpha 1 plus alpha 2, and f1 is equal to alpha 1 times 1 plus the square root of 5 divided by 2 raised to the 1 plus alpha 2 times 1 minus the square root of 5 divided by 2 raised to the 1. We can solve the linear equations from part 4, and we get alpha 1 is equal to 1 over the square root of 5, and alpha 2 is minus 1 over the square root of 5. And then we use theorem 1 to write the final form. And this is actually Benet's formula, which I think we got to discuss a little bit in CS141. And it was kind of this cool mystery, like, hey, how did Benet come up with this? And this is actually how Benet came up with it. So pretty nifty way to directly calculate any Fibonacci number using that equation. What happens if you only have a single root? Well, then we have a special version that's theorem 2. And the basically here we get only a single root instead of two distinct roots, in which case we use this form, alpha 1 R0 raised to the n plus alpha 2 times n R0 raised to the n. So it gives us a slightly different form. So here we have a sub n is equal to 6a n minus 1 minus 9a to the n minus 2, with alpha 0 is equal to 1 and alpha, or a1 is equal to 6. We use the same general outline with theorem 2 and work that out on the board, and we'll see two roots that are actually the same, and then we use theorem 2 to plug those back in. For higher degree polynomials, we'll use theorem 3, and this one again is worked out in the textbook. And this one, we have three different initial conditions because we have three different terms, and we'll use the same general outline with theorem 3. And this one is worked out in the text, and we'll work it out actually in class. When you have multiple roots that are not distinct, you use theorem 4. And this one is, again, one that will work out on the board, and it's worked out in the textbook under section 7.2. So, and make sure you take a look through these. We will work them out in class so that you see how they work. Solving linear but non-homogeneous recurrence relations with constant coefficients. For example, a sub n is equal to 3 times a to the n minus 1 plus 2n. We can basically more generally have a function f of n that's not identical to 0 and depends only on n, and then we come up with an associated homogeneous recurrence relations. And there are also particular solutions to non-homogeneous recurrence relations with constant coefficients that are covered to some extent in the book, but not really the focus. Linear but non-homogeneous recurrence relations with constant coefficients. These use theorem 5 to solve, and there is an example in the text. And this one is really, really tricky, but we'll definitely go over that in the text and in the class. And we basically need to solve this associated linear homogeneous recurrence relation and find a particular solution for the non-homogeneous part and then combine those. So for the linear homogeneous part, we have a sub n is equal to 3 times a to the n minus 1. There's a solution of alpha 3 raised to the n, where alpha is a constant. And then we deal with the non-homogeneous part of 2n. And we let pn equal cn plus d. And then an is equal to 3an minus 1 plus 2n, and becomes cn plus d is equal to 3 times c to the n minus 1 plus d plus 2n, and we can solve that and come up with a particular solution to this one. So what do you need to know from this? Because again, this is a very difficult portion of the textbook. Basically, there are ways of transforming linear homogeneous relations into closed form formulae. And they can be difficult to solve beyond those first two cases, theorem 1 and theorem 2, which is why I worked through the examples 1 and 2 in the presentation and kind of cover the other ones in class. We want you to be able to kind of work through those first two, and the other ones, if you encounter those somewhere, then you'll have to probably do a little bit more work than you might have to do for a class. But we'll give you the tools that you can actually solve them. So the particular form of the polynomial for linear but non-homogeneous recurrence relations with constant coefficients is given by theorem 6. And again, that's a very difficult one. And we'll have Chris Usher play you off here. Thanks so much for watching.